Welcome to Geology Talk, our monthly gathering of geology enthusiasts, brought to you by the Geological Society of the Oregon Country, the oldest collaboration of amateurs and professional geologists on the West Coast, we believe, and with ample support from the Portland State Department of Geology and the Beverly Vogt PSU Graduate Student Fund. We very much appreciate. Our panelists today, Andrew Dunning, and special guest Alyssa Smith is stepping in for Emma and Carrie Gordon and myself. And we'll have Andrew doing the geology news, followed by Dr. Matt Brunengo, who's going to be talking about his doctoral work on rain and snow events in the Western Cascades, something I know absolutely nothing about, but we're always fascinated to think about the relationship between meteorology and geology. And as our friends at the Don't Panic Geocast remind us, it's all the same physics, it's just a different time scales. So here's Andrew with the geology news.
This is the geology news for April of 2023. I have been exceptionally busy this month preparing my thesis and doing all sorts of other things that I'm perpetually doing. So this is a bit lighter than previous installments, but I think you'll still find it interesting. I will start with earthquakes. So the biggest event of this last month was a magnitude 7 north of Tuban in Indonesia. That's this guy right here. It's a very deep focus earthquake, 594 kilometers deep. So that's extremely deep as far as earthquakes go. So it was felt over a wide area, but not with particularly strong shaking. So there was no damage that I've been able to find any records of, so that's good. There was a similarly sized earthquake in Umbunti in Papua New Guinea right here. That one was just a few days ago. That was moderate depth, about 12 kilometers, but it had severe strong shaking at the surface, as well as some liquefaction. And there were unfortunately 8 deaths and 874 buildings were damaged or destroyed. One of the emergency managers of that city said that they got off easy. They got lucky with this earthquake, and hopefully recovery efforts will be swift. I forgot to change my text. I did not. Okay, so this is all earthquakes in North America greater than magnitude 2.5 over the last 30 days. The largest one was not North America, just the United States. The largest earthquake was a magnitude 6.0 off of Vancouver Island right here. This is a strike slip earthquake that occurred in one of the transfer zones. These are called up here, so it's not at all related to subduction zones. It was felt by just a couple of people right here on the northern tip of Vancouver Island. Here on the continent, the largest was a magnitude 4.4 in Cobb, a city I've never heard of, right about here in California. There was also a 2.8 in Wilderness Rim, Washington, right up here, and a magnitude 2 earthquake below Mount Hood just a couple of days ago. Overall, a rather unremarkable month in United States seismology.
There was a large magnitude earthquake near Panama. Is the Panama Canal in a seismically risky area?
Seismically risky is a subjective term, and I don't know enough about the geohazards of Panama to answer that. That's this earthquake right here. It is in an area of dynamic topography in that it is always under tectonic influence. And this whole land corridor, the Panama Isthmus, really only became land, I think between 2 and 3 million years ago. So it's very young, very active, very dynamic, and earthquakes are not uncommon down there. The Panama Canal is mostly composed of water and lakes rather than artificial structures. So generally earthquakes are not an enormous concern of theirs, except for in the lock structures. My understanding, I'm not an expert on Panama Canal engineering, but my understanding is that the most recent upgrades to the Panama Canal have alleviated most concerns of seismic hazard. little bit more of an exciting month for volcanoes around the world. There are 28 ongoing or new eruptions as of this morning, with substantial activity at Rincon de la Vieja in Costa Rica, where there was a pyroclastic flow, which is pictured right here, and a number of rather large steam eruptions. Very minimal impact to the surrounding community on these volcanoes in most of Costa Rica. Kilauea is doing its normal on again, off again sort of activity, and there were earthquakes and signs of magma intrusion just a couple of days ago. And then also just a couple of days ago, it said, nah, never mind, I'm not going to do anything. And now the summit is quiet once again. There was a major eruption in the Kamchatka Peninsula in Russia of the Shiveluch volcano. There was a major ash emission that actually disrupted a number of trans-Pacific flights that go over the Aleutians to really between North America and Europe and Eastern Asia, Japan, China, etc. The ash here is not quite as heavy as it looks. It's blanketing the fresh Russian snow. So the impact to the local community really amounts to little more than a big mess. But the ash eruptions of the volcano were actually quite spectacular. And there's some really neat pictures floating around online. I harvested this one off of volcanodiscovery.com. And if you heard a few months ago on the news, there was some unrest going on at Trident Volcano in Alaska. There's still no change to that. Nothing is going on up there as of now.
So Andrew,
yeah.
just a moment ago, you mentioned pyroclastic flows with one of these eruptions.
Yeah.
So what exactly is a pyroclastic flow, and are those common with certain kinds of volcanoes? Do we have that danger with every volcano or just some of them?
Yeah, so pyroclastic flows are common on a lot of stratovolcanoes, which is Rincon de la Vieja is one of. This is a subduction zone arc volcano. This is very much like the ones we have up in the Pacific Northwest, though not quite as tall. And when a volcano like this erupts and all of the molten rock basically exsolves into gas, the many fragments of that molten rock then coalesce into these density currents, these incandescent clouds of rock and steam that hurtle down slopes at alarming speeds and are often the most dangerous part of large volcanic eruptions. This one was pretty minor, didn't really cause much beyond what you can see here in this picture. So that's good. What was the other half of your question?
It was basically, do you expect these at every type of volcano, or are they just at some?
Just at some volcanoes, generally speaking. At ones like Kilauea, pyroclastic eruptions are exceptionally rare, and there's only one in recorded history at Kilauea. So basaltic volcanoes like Kilauea tend to erupt fluid lava that's sort of like pouring molasses over the landscape, except if you stuck your hand into it, it would melt rather than just get sticky. So pyroclastic flows are what we expect from eruptions at most of our Pacific Northwest stratovolcanoes, our biggest ones. We move on to some research news now. This is a fun one that I discovered on subsidence of the East Coast. So high-resolution digital elevation models derived from 13 years of satellite data show that there is widespread subsidence of the East Coast. So that's the ground surface sinking and getting lower over time. And most of the eastern seaboard is sinking at an average of 3 millimeters a year, but there are parts of it that aren't moving very much, like up here in Boston, or surprising to me, at least over here in Florida. But there are other parts like here in the Chesapeake Bay where those rates are much, much higher. Like up here, it's 6 millimeters per year in this sort of exclave of Virginia. I can never remember what that area is called. But the thing that these researchers were most alarmed by this is that it shows that the eastern seaboard may be a lot more susceptible to threats from sea level rise than previously thought. This sort of large area, wide-scale subsidence had never been calculated until recently, so a lot of coastal sort of threat management models have not taken this into consideration. This is a result of sediment compaction The East Coast is what we call a passive margin, which means that all it does geologically really is just collect sediment over time. And that sediment collapses or compacts as water escapes from it, and your different mineral grains settle and pile on top of each other. So this is completely natural. This has been going on for as long as the East Coast has existed in its present incarnation. So really, it's just interesting from a modeling future climate change hazards perspective. Any questions on that?
Well, it was more of a comment I had, is it's going to be interesting to see how these data are incorporated into studies of hurricanes out in this area, because it's kind of like if you're already getting impacted with all of these hurricanes and now you have to, you know, kind of consider subsidence as well. Like, I don't know if they're going to change anything about the way where they engineer things on the coast. I mean, people have vacation homes butting right up against the sea there. I don't know, hopefully this is helpful.
I hope so too. But I was just thinking, so over the last 100 years, if that averaged 3 millimeters per year, and that's over 13 years, so 100 years of that, that's, what is that, 30 centimeters? That's a foot. So that's a good clip. That's equivalent to parts of our coast are moving, but that's all due to tectonic activity rather than compacting sediments. That's a good clip, especially that part of the Chesapeake Bay area. All right, Newport-Inglewood Fault. One of my favorite faults is an active fault down in Southern California in the Los Angeles Basin. I should have thrown a location map in here, but I neglected to do that. But anyway, this project distributed a few high precision, extremely high sensitivity seismic arrays throughout the Los Angeles Basin. And they were specifically studying microseismicity. So that's really small earthquakes, usually around or less than magnitude 1, which is, I think the equivalent energy of a number of hand grenades. So these are very small events at very shallow depths. They were mostly detecting very small earthquakes in the uppermost 2 kilometers of the Los Angeles Basin. So it's really high precision. That's where seismic noise tends to be the highest. It's really hard to detect earthquakes in that upper 2 kilometers of the earth, especially in a place like the Los Angeles Basin, where that upper 2 kilometers is mostly sand and mud. But anyway, the Newport-Inglewood Fault is one of the most important faults in really in seismic history. So it had a magnitude 6.4 earthquake in 1933, which was highly damaging. It devastated the Los Angeles Basin and was really the impetus for some of the earliest modern seismic building codes. The destruction was so severe that engineers decided, hey, wait, we can actually figure out how to engineer against this sort of stuff and prevent future earthquakes from being quite so devastating. It's an interesting fault. It's buried, so it doesn't reach the surface. We cannot find exactly where the trace is. And it turns out a part of that is that the upper 2 kilometers of the fault zone widens. It's like a flower. And at the surface, it's more than 1 kilometer wide, this fault zone. So that's this whole A to A prime section. That's how wide the fault zone gets near the surface. And all of these little tiny earthquakes are occurring in that zone. This is just a little seismic swarm that occurred out here at the mouth of the San Gabriel River. This is the city of Seal Beach, if you're familiar at all with the geography of the Los Angeles Basin. They did a number of these transects throughout the Los Angeles Basin, including on the Garden Grove Fault, which is actually this one right here. Their transect was located a bit further north than this image. And it really confirmed and helped clarify the complexity of these shallow faults and how they express near the surface in the Los Angeles Basin. So understanding the way they blossom out and get wider to the surface helps us understand where damage zones are most likely to be in the event of future earthquakes.
I'm going to butt in again since you're an earthquake person. So a lot of the time when we learn about faults and stuff, we think of them as just lines on the surface. But a lot of the times those do tend to be wider zones. So with these smaller faults, is that typical to have them be set so wide, or is this pretty unique?
This is wider than normal.
Okay.
And part of the reason is because the sediment in this uppermost part is so soft and easy to deform. Faults like to form planes where in really hard rock, where there's a lot of pressure confining all that stress to a single zone. And as you get closer to the surface, those confining pressures decrease. And so the stress is able to distribute or diffuse out over a larger area. And that's very common. Usually those fault rupture zones are on the order of a few meters, like, I don't know, 5 to 20 meters wide, but a kilometer is definitely bigger than is generally expected.
Got it. Does the amount of like structures and stuff that's like, this is a very population dense area, does that have any effect, or is that too like small scale to really impact?
I don't know. I know most of the concrete and aggregate we use in the built environment ends up coming from pretty locally, interestingly enough. The Los Angeles basin is filled with old sand and gravel pits that have been filled in. So I guess the overall regional weight loading probably hasn't changed all that much. But generally, the built environment does not impact the actions of the deeper interior.
Sure.
Generally. All right, I'm gonna move on. This is the thing that probably most people have heard about in the last month. Pythia's Oasis is an area of thermal springs near the bottom of the Cascadia subduction zone trench off the coast of central Oregon. This is an area of warm water springs which is releasing water from fault zones according to temperature and chemical analyses. The Cascadia subduction zone, where the Juan de Fuca plate off the coast, is diving underneath North America, and it does so at an angle. And because it comes in at an angle, the subduction zone ends up getting, one author called it cross-hatched by these vertical strike-slip faults, kind of checkerboarding. And these strike-slip faults allow stress to move around in different sort of funky ways. But most interestingly, as a result of this, they call it a fire hose of thermal water. Let me back up here. This is a fire hose of thermal water as described by the authors, the researchers. It was discovered in 2014. For some reason, they say that it was in 2014, but they also call it a new discovery. Generally, it's a very weird, bizarre paper. And as a result of its weird, bizarre writing style, all of the clickbait fake news sources called it an impending harbinger of earthquake doom in the West, or whatever stuff they come up with. But this is a vent of hot water 5 centimeters across, so it's about this big. And it's just spewing out water that is only a little bit warmer than the surrounding seawater. It's 12 degrees Celsius, so that is about 50 degrees Fahrenheit, much too cold to bathe in. But they do agree, and they argue that this is fluid escaping from an overpressurized fault called the Alvin Canyon Fault, which is a vertical strike-slip fault with lateral motion, which I mentioned. And if fluid is indeed escaping from that fault zone, that suggests that it is overpressurized and fluid is escaping, which causes friction to build up much more. So when the fault zone is saturated with high pressure water, it is experiencing a lot less friction and is able to sort of adjust and shift without causing earthquakes. Now, when you remove the water from that situation, it tends to lock up a lot more. But, and I want to stress this, this is not necessarily indicative of anything beyond normal. We do not have long-term observations on this one site. Other sites like this are all over the place around the world. This just happens to be the warmest one we've found on the Cascadia subduction zone. Here's a model of how this water is sort of moving around down there. So down here you have the basement rock. This is your oceanic crust. This is your basalt, your serpentinite, your hard, dense, cold rocks. And the fault plane extends somewhere down into there. This is a stratigraphy that we are able to determine from the way seismic waves are bent and refracted through sediment and rock under the water. And so the oceanic crust is able to circulate a lot of seawater through because there's a lot of seawater above it, and oceanic crust tends to be sort of fractured just by the nature of the volcanic origin of oceanic crust. So it allows a lot of water to circulate through. And as this water gets squeezed out and rises along the fault zone, it gets other water into it from compacting sediments. This is the décollement. This is the actual plate boundary. This is the Cascadia subduction zone plane, or at least they're interpreting it as that. This shows the relative geothermal gradient called the geotherm. So the water's hot down here, but by the time it gets to the surface, it is much colder, on the order of 12 degrees Celsius, and loaded with minerals and other stuff from this thick pile of rock and sediment it had to rise through to get to the sea floor. So they said in the paper, we think this is rising from an overpressured fault zone, but they also said we cannot rule out that it is just escaping compaction fluids from these rocks. Really, really bizarre paper that I have problems with, but you know, whatever. I'm not an expert in sub-oceanic fault zone fluids. I imagine there's probably questions about this, so let's discuss.
Okay, so one of them is this diagram. What is the MBSF depth unit?
Oh, it's meters below sea floor.
Okay, got it. Sounds good.
I do know.
And just as an aside, one of the other comments is, at some point, would it be possible for you to list some of the sources for your geology news?
Oh, yeah, I usually do, but I didn't.
That's okay. So now I have an interesting question about this, because having done a lot of groundwater dependent ecosystem surveys on land, not in the ocean, the temperature you're talking about here is pretty standard for spring temperatures. It's groundwater temperature.
Yeah.
So I guess for me, I'm seeing what I was seeing is something similar to what I have found out here in the Ochiko Mountains for spring, spring surfacing. Is that same sort of small diameter, instant water gushing out of it. And so I see this as, oh, hey, we picked up on a groundwater dependent ecosystem, and look at all the critters in there.
Yeah. Apparently their surveys said that this was somehow uncommon.
Well, see, I think observations like that kind of illustrate how important it is for people of different subfields of geology to have conversations, because I may be talking about something with volcanoes, and then Andrew's listening and he's like, okay, well, here's this perspective about earthquakes. And then Carrie, you've got the perspective of groundwater. It's like, we all tend to do our science in a bubble, when really, if we just kind of have those conversations, we can make those connections that are really valuable. So just a little aside.
Very true, very valid. Any other questions on this? Well, if not, then that's all I've got for this month, and I will see you in whatever next month is, May. Thank you very much.
Wonderful. We're looking forward to that. Thank you, Andrew. And thank you all for the conversation too. That's one of the delightful things about having, for those of us who are amateurs, getting to listen in on the conversation about among those of you, especially those of you who are at the forefront of the science, those of you who are graduate students. Alyssa, I didn't really introduce you. You got to introduce yourself was it last month or the month before?
I think it was the month before.
The month before. Yeah. But do tell people who the heck you are and
sure. Yeah.
what you're up to.
Sure. My name's Alyssa. I'm a second-year PhD at Portland State. So I previously did my master's in Arizona. I went to Northern Arizona University, and before that, I did my bachelor's at Sacramento State, and before that, I did my associate's degree at Modesto Junior College. So just been a lot of schools over the years. But yeah, I study the chemistry of volcanic systems, and specifically trying to figure out where magmas in the central high Cascades have come from. So that's what I'll be working on for the next couple of years.
And am I correct that you have an interest in just science communication and geology education generally?
Absolutely.
So
yes, absolutely.
You may be geology's next Pamela Gay. I'm not sure, but hopefully we'll have you back. And thank you for all your questions today.
Sure. Yeah. I'm glad to be here.
I'm going to introduce our special topics. It's almost perfect timing, by the way. It's 11:30. I'm going to introduce our speaker, special topic speaker today, Dr. Matt Brunengo. Some years ago, I don't know, 4 or 5, we went to the Department of Geology faculty meeting and said, we're doing a Portland field trip, or a series of Portland field trips. Who knows Portland geology best and is sort of really a lover of the area and can give us some of the history as well. And they said, faculty all said, you got to talk to Matt. So we recruited him for our Johnson Creek field trip, which I may have mentioned in the pre-show and probably will mention again, and also for the Clackamas Basin field trip. And so he's helped us with those. And then recently he's done a sort of geology overview course, which maybe he will describe, and I'll let him talk a little more about himself and his background and what led him to his doctoral work. Matt, thank you for joining us today.
Well, thanks for having me, and that illustrates the danger in not showing up to the faculty meeting, that you get volunteers for all kinds of other things.
Yeah.
So I'll just say, I grew up in Portland. I went to college at Stanford, and then I went to grad school at University of Washington, which is where I started the project that I'm going to tell you about way back in the previous millennium. But I came back to Portland to come to Portland State to finish the project. I've taught at Portland State off and on. I've done a little bit of consulting work and things like that. So I guess that's my story. Okay, this is to get your attention. Little known killer in the north, rain on snow. Unfortunately, I don't have any pictures of bloody carcasses on the tundra, but mostly it's charts and graphs. So anyway, okay, this was, as Paul said, this was my PhD project that went many decades with a big hiatus in between. That's hell freezing over in the background there. It's from an old edition of Dante's Inferno, where actually the final circle of hell is frozen. It's not hot. But there's the title, and down in the lower left-hand corner is a link, and I hope to make this PowerPoint available. There's several links in here. Some of them are hot, some of them are just URLs, but that was to a talk I gave 10 years ago, about a 20-minute talk, that if you're more interested in this thing, you can get that version of it as well. Okay, what is rain on snow? This is, by the way, this is not exactly geology. It's kind of geology adjacent, hydrology, and especially snow hydrology. But if in the back of your mind, you keep thinking this affects flooding and this affects landslides, then we're pretty much there. Most of you know what this is. Snow melt during rainfall, sometimes really big events, where warm temperatures raise the snow line, and melting takes place as well as rain. The combination of rain and melt can be major inputs in the Pacific Northwest and other places. Contrary to the name, the rain doesn't cause most of the melting. That's other major energy sources are sensible and latent heat, long wave radiation, not sunlight. This is cloudy winter, half the time it's dark. But the rain contributes some of the heat and most of the water. Where does it occur? Commonly in maritime temperate climates like ours. Western North America, it's very common. winter storms coming in from the Pacific when there's snow in the mountains, maybe even in the lowlands. And so especially in middle elevations. Here's a satellite view from the 1996 storm floods, which is in living memory of most of us, many of us at least. I did want to go at this point to talk briefly about atmospheric rivers. There's a link to a Wikipedia article. There's a link to a NASA video explaining the phenomenon. This middle link here is a 10-day loop of essentially atmospheric rivers all over the world. Most of you know, I'm sure, that especially in the Pacific Northwest, we have some, besides just the atmospheric river rainfall coming in, we've got the topography, several sets of parallel mountain ranges, the Cascades, the Coast Range, even to the Rockies, where prevailing winds bring in moisture. The moisture condenses and falls off on the west side as rain or snow, and then in the rain shadow, it's much drier. Besides that, there's some secondary topographic effects, like, for instance, the Puget Sound convergence zone of winds that are coming around the north side and the south side of the Olympics and causing rain bands to the east. And in my case, the area that I'm working in, I worked in down here, rainfall or big winds and moist winds coming in from the Pacific through the Chehalis Gap south of the Olympics and kind of parallel to Olympia and into the Cascades that way. So there's secondary effects. That's where. When does rain on snow occur? Quite often it's seasonal in the winter, fall and winter and early spring. Frontal cyclonic storms come in from the Pacific. Atmospheric rivers, one subset of those is Pineapple Express. Warm air holds more moisture, so warm air can deliver more rain or snow in that case than cold air. Most in fall and winter, where rain is the greatest component. Excuse me, some occur in the spring, and atmospheric circulation patterns affect these things. There are no specifically rain on snow storms. Many things affect how these things happen. I'll let you read this while I talk for a minute. The first one seems to have been the first one that seems to have been recorded by Euro-American settlers in the Northwest was in 1853. The Columbian used to be a small newspaper in Olympia before, I guess, it moved to Vancouver. So it wasn't even Washington Territory at that time. It was Northern Oregon Territory. But a big storm took place in that year. Ezra Meeker, who then moved to Puyallup and became the Hop King, was trying to settle at Kalama. And he and his brother wrangled a bunch of logs that were floating down the Kalamba River, put them into a raft, and sailed them down to sell them to a sawmill down by Astoria for a few $100. Major rain on snow events in the Pacific Northwest. I don't think any of us can remember the Wellington avalanche disaster. That was mainly a snow avalanche, but rain on snow was involved. The Vanport flood, the Memorial Day, 1948. This picture from a USGS publication was kind of the beginning of Portland State University. Even downtown Portland was back flooded by this flood. This is 10th and Hoyt in Northwest Portland, almost to the railroad station, where water was in the streets. Lots of other storms. The Christmas flood of 1964 was the one I remember when I was a kid. Please excuse the bad photograph. He was only 9 years old and it was a new camera. But this is the steel bridge with the lower deck raised so the floating houses can go by, not to mention the water. Lots of other examples. 1980, a debris flow on Mount Hood killed a camper. 1996 was the most recent big one. This is the Willamette Falls being flooded out. This is the day after the rain stopped and the sun came out, but obviously a whole lot of water coming down the Willamette. Most rain on snow events aren't catastrophic. We remember the really big ones, the 1964 and the 1996 and things like that. Again, too much text, but these things have been recognized since the 30s and 40s in the Northwest. This was a talk and a paper given in the the American Geophysical Union in 1940, talking about the preliminary explorations for flood control dams in the Puyallup and White Rivers and Green River. So even then, it was recognized that heavy rains on top of snow that melts part of the snow was the cause of much of the flooding. Okay, why does it matter? It's important water input process, in the Northwest. It changes the snowpack storage and runoff relation. It affects people and our stuff, landslides, avalanches, transportation problems, and in some cases, people affect the processes, land use and climate change. I hope to have time to get to at the end of this talk. So hydrologic significance, rain on snow relative to simple precipitation. If this is a rain gauge and all this snow is being piled on top of it, the rain gauge isn't really telling us what physically is happening. Is it rain? Is it snow? Obviously from the picture, it's snow. Even if it's a heated rain gauge, then it's just melting all the snow into water. We still don't know what's going on. What's really more important is what goes into the ground over short time periods, days to weeks. This is a snow lysimeter, which is basically a big pan to average out the snow coming through the canopy, but it also measures, it goes into a gauge somewhere that measures the amount of water that's coming out of the snowpack, which is the thing that's important to the soil and even downstream. So hydrologic significance at the trivial end, maybe a little rainfalls on the snowpack. It starts snow metamorphism, doesn't really do all that much. When some of the water actually leaves the snowpack, then it starts to become more important. And this acronym WAR, infelicitous acronym, water available for runoff. So to me, that's what's coming out of the bottom of the snowpack at a given time. And then when it gets to the significant end, it's where the water available for runoff is greater than even the snow precipitation was. So we're getting not only the rainfall, but also some component of snowmelt. Question, how much, how often, where does it happen? That's kind of where I was getting into this sort of thing. And I'm not the only one who works on this, obviously. A really quick look at, a cartoon. If this dark blue line represents the snow line or the depth of the snowpack at the beginning of an event, a rain on snow sort of event. And then as it rains at lower elevations, it might still be snowing at higher elevations. You get accumulation up there, you get melt down here. The difference in the amount of water going into the ground can change from no difference because there was no snow, it's just the rain going into the ground, to no water going into the ground up at high elevations because it's all snow. And then in some middle elevation where the snow melt is contributing to the water that's going into the ground. And that affects the hydrographs, and it also affects the frequency diagrams of these sorts of places. This is the area for this particular storm where it was a significant rain on snow. That elevation, that place moves up and down continuously. So possibility of using the instrumental record to study these sorts of things. Unfortunately, we don't have rain gauges and snow gauges and temperature gauges everywhere. The weather surface gauges tend to all be towards low elevations. The snow survey and snow tail sites, I'll show you pictures of a couple of these in a minute, tend to be at the high elevation sites. They have a limited record length, maybe 70 at tops. So the instrumental record is pretty limited to examine these sorts of things. Okay, so study that I sort of put together again over many decades, started working in the Seattle and Tacoma municipal watersheds, a data-rich environment. If you look at this map here, here's Seattle, here's Olympia, Portland is off the south, and we'll home in a little bit south. This is the area that I worked in mainly because there were so many different kinds of data that were available. As I said, 2 municipal watersheds, 1 hydroelectric plant project, flood control projects on the White and the Green Rivers, and a lot of snow survey sites and courses. In this picture, the red diamonds are weather service stations, co-op stations, with hourly precipitation, which is what I needed. And down here in the almost on the right edge is Stampede Pass that I'll talk about in more detail. The yellow pentagons and stars and crosses are snow survey sites and snowtel sites, which is more recent. Records I used for this were from 1940 to 2005. The terrain looks kind of like this, looking up the Cedar River towards where the reservoir is. And it's kind of a generally a simple ramp up the west side of the Cascades from west to east. Ignore this, this is over the crest, low elevations and high elevations. But even so, there's a lot of variability in the terrain and in its effect on rainfall. This is annual precipitation. Mount Rainier is very high. Alpine lakes in the North Cascades are very high, lower in the Puget Lowland, as you'd expect. But even within the mountains, there are little rain shadow effects in the deeper valleys. So I'm smoothing over a whole lot of stuff in here. Okay, Stampede Pass, the best station to work with because it was a high quality, generally staffed observation station all year, every day, measurements, except when there were periods when Congress cut the budget and then they went all instrumental, and usually those were disasters. But anyway, here's the weather station up near the crest of the Cascades, a very low place in the crest, only 4,000 feet. Temperature, precipitation, wind, snow, lots of measurements, hourly or better, almost continuous since the mid 40s. And this is the snow survey site, snowtel site, where this little gray pad here is a pressure, a weight-driven pressure transducer, and the little rocket-like things that you may have seen in the woods are storage cages. So that's Stampede Pass on the crest of the Cascades. Here's Snoqualmie Pass, where I-90 passes over, so it's a little bit south of there. Lots of precipitation data. I'm not going to talk about precipitation very much, but all of these marks represent measurements during the record from 1 hour precipitation. The highest one there was about 1.1 inch in an hour or something like that. At 48 hours, we're talking about, what's that, 30 centimeters, about a foot, about 12 inches. And these long continuous storms that I was really looking at, where there was practically no breaks in precipitation over a long period of time. I think this one was something like 20 inches in 11 days. Wasn't all rain, but at least it was precipitation. Okay, a little digression. Ways to measure snow, ways to quantify snow. One is snowfall, and that's the daily accumulation measured on a snowboard, usually at a weather service site. So when Portland had, I think it was 10.8 inches of snowfall at Portland Airport in February, that was one day, and then they cleaned off the board and started counting again the next day. Snow on the ground or accumulation is a little bit different. So that's at the total depth at a given time or day. Mount Baker ski area had the record. I think they still have the record for the largest annual snowfall, which was, I think, something like, it's in the notes here, I'm not going to look, 1,140 inches over the season. Now, if you divide that by 12, that's 95 feet. They didn't have 8 stories of snow at the ski area. So that's an accumulation of daily measurements as opposed to measurement on a given day. Some of these are measured manually or instrumentally at a station or by snow survey. That's where they drive a little tube into the snow, bring up a core and then weigh it, or at snowtel sites. And then, snow water equivalent is what most of the rest of these graphs are going to show. That's the amount of water that would be yielded if you took the snowpack and melted it, or when you melt it. So a lot of these graphs will say SWE, mostly in centimeters, but that's what those are about. So here's the snow measurement sites. 20 snow courses where people drive tubes into the ground, or have been since the 30s. 8 snowtel sites in my study area. Many of them are at the same place, and I only use the ones that are greater than a 10-year record. So some of them were too new for me to use. This is a link to the Natural Resources Conservation Service snow information webpage, where you can find out what the, I will allow you to look up this link in your at your leisure. Anyway, Cooperative Snow Survey and the SNOTEL sites give us a lot of information about snow, especially potentially hourly, certainly daily, instead of just once a month. Move along. Since Paul showed you a version of this graph, I'll show you this one. This is a combination for Stampede Pass, that place up at the ridge, up at the crest, at various kinds of information. One of them is the National Weather Service measurements. You can kind of see the maximum and the minimum and the average. The little diamonds and squares are from the snow survey. So those are, at least up there, they were taken about twice a month through the year. And then the SNOTELs, which have been around only a few decades, well, since the early 80s, those are basically hourly to daily measurements as well. So you can see, and this is snow water equivalent for Stampede Pass. We're up at 200 centimeters at the maximum, and that's the water. That's not the net depth of the snow is probably going to be 8 or 10 times deeper than that. And the average, where the average takes place sort of around now, early, late April. By the way, these dates are not calendar days, they're water year days. So one is October 1st. So there's October, there's November, December, January, February, March, April. So this kind of end May. You'll see a version of this later on, if I get that far. So the problem is rain on snow events vary with climate, terrain, vegetation, all kinds of things. The observational record is too short. And so my project was to use some probabilistic modeling to quantify rain on snow over the long term. Monte Carlo methods just means using random numbers to do sampling and run virtual experiments, compensating for sporadic events and scattered station. The model is really simple. I did it in Excel workbooks and Visual Basic Code. Some parts of it are probabilistic, some, which means sampling from random numbers. Some parts were physical or deterministic, like calculating snow accumulation and melt and allowing for the percolation of meltwater to the ground through the snow. I'm not going to, I've learned not to go through this. This is an entire separate hour talk. But anyway, I would run each model for 1,000 years, 1,000 hypothetical years, which gave me about 4,400 events. This is why I don't generally show this much anymore. The code is about 20 pages long, typed out. Assumptions, a constant climate for 1,000 years, no way, but that's the assumption to get some numbers that are more useful for 10 or 50 or 100 years. Simple code, and it's based on events and sites, it's not continuous. And here's where I skip ahead, since it is now 11:56, and hope for a miracle. Just to show the model reproduces the ruling equations. For the most part, these are model outputs for precipitation at, let's say, Stampede Pass, although there are some outliers. That happens when you're playing with statistics. That means I broke the bank at Monte Carlo on that particular day, or vice versa. Here's the one that Paul showed earlier. So that's the graph. Most of the lines and symbols here are the graph I showed before. All of these little blue dots are the 44 outcomes for starting snowpack at Stampede Pass out of the model. So yeah, they cluster in the late fall and early winter and winter to early spring months. Many fewer in the spring or in the early fall. Some of them are higher than we've seen maximum before, but again, that's probability. That in 70 years we can't pretend that we've seen every possibility so far. Okay, so to get to the results, there are many ways that the output of the model seems to work. The output of the model can be evaluated to answer my questions about frequency and magnitude and importance and significance. This is the one that I think is the simplest. Each of these squares or circles or whatever they are represent a model run at a particular elevation. So 200 meters, 250, 300 meters, up to 1500 meters. There are four possibilities in the model and in nature of what can happen in these events, or the proportion of things in the events. One is that the, let's say the green line, that the amount of water that goes into the ground is equal to the precipitation. So the rain falls on bare ground, or a little bit of snow happens and it melts, and it all goes into the ground. So that's the green line smoothed out. It's the greatest proportion of events at low elevations and falls off as you get to higher and higher elevation. Extreme is where no water gets to the ground. In other words, either it's all snow falling or some liquid water gets soaked up by the snowpack. So that's what happens generally more often at higher elevations, a greater proportion. By the way, each one of the four symbols in any one of these models has to add up to 100%. There's a, that's 100% of the possibility. The red line here is where it's somewhere between 1% and 99% of the precipitation goes into the ground. But the one that's really interesting is this purple line down here with the hump. This is where the water available to go into the ground is greater than the precipitation that fell during the events. And this kind of maxes out at about 20% of the events at about 800 meters. So this is looking like the place in this area based on this model where rain on snow is most. Skip over this one since I see we're getting short on time. My clock says 12 o'clock. The elevations, again, where kind of rain on snow seems to be more frequent and more important, tend to be, if this is an elevation curve called a hypsometric curve for my area, tend to be between about 500 meters and about 1100 meters. But that makes up between, if you subtract 70% minus 20%, that's 50% of the landscape in this particular area. Okay, so statistically it works. The maximum frequency and hydrologic significance, preferred zone 500 to 11, peak at about 800. So just quickly, I also ran this model in a few climate change scenarios. Temperatures rising, we know, snow volumes declining. Precipitation, the models are some are more, some are less, so I left that out. So basically adding 1 degree, 2 degrees Celsius, 5 degrees Celsius. So come back to this curve, which you saw before. Now, what seems to be happening in these different scenarios, a little warmer, maybe this is where we already are, a lot warmer and a lot warmer, that the rain on snow peak elevation is moving a little bit uphill, but it's becoming a lot more common. Instead of 20% of the events, now we're talking about 60% of the events. So in the 21st century, what seems to be happening, we've got this graph before, now the preferred rain on snow zone is moving uphill. And the effects, therefore, are liable to move uphill as well. This doesn't mean that rain on snow big events won't ever occur at sea level, like 64 or 96. It just may mean they're a little bit more rare than they were before. So the conclusions are differences among many events over a long period of time. The preferred rain on snow zone, based on 1940 to 2005 data, peaks at about 800 meters. By the way, that's about 2,500 feet. So in many events, the ground feels something different from the precipitation that falls into a rain gauge, whether it's a heated rain gauge or not. And the differences will increase from lower to higher elevations. We can change the scenarios. And just a quick shout out to the reason I started this in the first place was the forest management and land use implications are the changes in vegetation, i.e. wildfires and logging, changing the rain on snow frequency and magnitude situation in the Cascades. That got dropped off the project, or I'd be working on it for another 50 years. But there are differences in the snow accumulation and melt rate in openings as opposed to the forest. So any questions I can entertain.
Okay, great talk, Matt.
Thank
And
you.
I know that was a lot of information. Having worked in this arena for my career, folks, believe you me, he had a lot of information. It's okay. We can break it down into bite-sized chunks that now you know what a rain on snow event is, and then think about it as you're driving over the pass next time. So we did have a few questions in the chat. Back at the start, you talked about snow lysimeters. Are they unique to a specific research project, or are they part of the standard array that we see, like Stampede Pass or some of those other sites in your study area?
No, these are generally research level instrumentation. So this picture, at least according to my notes, I didn't remember that, was from H.J. Andrews Experimental Forest east of Eugene in Willamette National Forest. So these would be put out and instrumented, specifically for a research project. I tried to build these in a field area in the Green River, and mine never really worked very well. But yeah, these are not common instruments around the landscape.
Okay, and there was that was my experience too, but that was a really good question that we had. There was a question too. You briefly mentioned the Wellington avalanche, and I know that there's some very good books, and I wrote that into the chat, that have been written about that avalanche, and it was fairly catastrophic. Can you just give a little brief when and where it was, and maybe something about the size of the event?
Sure. I think the book you're thinking of was by Gary Christ, K-R-I-S-T, White Cascade. Bad year for the Great Northern Railroad. Well, this was before the big fire in Idaho Panhandle. A bunch of trains got stuck, delayed on the west end of the Stevens Pass Tunnel, the old Stevens Pass Tunnel, on the where it crosses the North Cascades heading to Everett and Seattle, because of a huge snowfall on the west side. I think there were 3 trains. There was a railroad, essentially a small town there with cafeteria and lodging, and basically it was a station area. So the trains were stopped. They were coming from Spokane to Seattle, kind of waited around for several days, and they couldn't sit in the tunnel because there were steam locomotives, and that would, asphyxiate everybody. So they were out on the west side, and after several days of heavy snowfall, a rain on snow happened, some thunderstorms, some big avalanches came down, swept, I think, 3 trains into the canyon, where most of the people were hanging out in the train cars, waiting for the track to get cleared. I think the official death toll was 96, but it was probably more like 100. It was the largest, most fatal semi-natural disaster in Washington state history. So the reason they don't know exactly how many people were there, but because they'd hired unemployed workers from Everett to come up and try and shovel the snow off the tracks, and probably some of those were killed as well. So yeah, that was rain on snow was a part of it. It wasn't the biggest part of it.
Right. So Kate has a question. Does this shift to the higher in elevation mean more or less runoff? We had epic floods in Northeast Oregon, February of 2020, which far exceeded the 1996 rain on snow event.
In some places that would be true. It's going to, if you imagine the rain on going the peak rain on snow zone, again, it doesn't mean it will never happen anywhere else. The peak rain on snow zone getting so high because it's so warm that it's above the crest of the Cascades, then it's not going to be as important in those places anymore. So from one place to another, the importance is going to be different in any given event, let alone over time. That 1948 flood, we call it the Vanport flood in Portland, but it was really a huge upper Columbia Basin flood, was a little bit like this year. It was a late spring. Instead of the snow starting to melt up in Montana and eastern Washington and Idaho in April, it was cold, it persisted. And then in May, the warm monsoon storm started coming up from the Gulf of Mexico and melting a lot of snow very quickly. So that, when people have written papers about that, they call that something like a 500-year. But it certainly had implications even downstream in Portland, where there wasn't really any rain on snow, but the water backed up from the Columbia to the Willamette. This year, the melt is late, but if you remember, no, you didn't get to see it. That map of the proportion of average snowpack in various basins. In the upper Columbia, it's kind of normal to maybe a little below normal, as opposed to what it is in California and Nevada. What's liable to happen now in California and Nevada as we get into spring is all that snow is going to start melting because of higher temperatures and more sunshine. So that's where the flood danger is liable to be this year in the Western United States.
This is pretty out of my wheelhouse, so hopefully my questions are not silly. But one thing I was thinking about is with these events, like what is the time scale from like the beginning of like a storm to when we start to see flooding?
Well, generally, the longer it is, the more likely it is to cause flooding. The storms in my instrumental record that I used to create the model, I sort of cut it off at 12 hours where something is falling out of the sky. And some of the ones, like I said, in the record, the longest one I saw at Stampede Pass was something like 11 days in which there was no gap in precipitation of 6 hours or more. So that's a long time. Most of them were in between. Most of these kinds of events last, the ones that are significant last 2 or 3 days. The 1964 storm, it was cold and frozen. I saw Scott Burns was here. He'll probably remember this. It was cold and frozen, like 0-degree temperatures in Portland, 0 Fahrenheit, up until I think it was a Sunday night, Monday morning. It turned around, the temperature went up to 50s and it started pouring down rain. Things like Johnson Creek, small basin, flooded. Clackamas River, a bigger basin, took 2.5 days to reach high water, peak water. And the Willamette, bigger basin still, went, I'm going to say 3 days from the 22nd to the 25th, where it peaked. So again, the size of the basin is going to affect when and how much the flooding takes place.
Got it. And are these usually associated with a really abrupt change in temperature? Like,
well, usually the really disastrous ones tend to be, because that means that snow was on the ground to sea level, let's say, like 1964 and 1996 are almost to sea level. And then the weather turns around, it gets really warm and rainy. So that snow at low elevations is the most vulnerable. That's the stuff that melts really quickly. In 64, even at government camp, I think they melted a 4-foot snowpack in 2 days. But certainly I lived at 1,000 feet in those days. Between Sunday night and Monday morning, several inches of snow disappeared. 1996, probably the same way. Snow level wasn't quite as low that year, but same sort of thing happened.
Got it. I had one more thing I was kind of thinking about. So you said that a lot of the time these events happen at kind of the middle elevation, and that tends to be where there's a kind of a gap in the data. So if you had to choose what kind of instrumentation you would put in that range to kind of bolster the data set, and just like a wish list, what do you think you would wish for in that situation?
I guess I would wish for something like I stumbled into for this part of the Washington Cascades, because like I say, municipal watersheds, hydroelectric projects, flood control projects from the Corps of Engineers. So they needed to know how much water they were dealing with. That's why there was so much data in that area. And a lot of those measuring stations have since been decommissioned. So yeah, like I said, the weather service stations tend to be in the lowlands where the people live. A few exceptions like Snoqualmie Pass and Government Camp. The snow survey, snow tell sites tend to be at higher elevations where the snow happens, although they are sort of making more and more a little bit lower. So if you were going to do this in a particular place, Mount Hood Corridor, Clackamas County, Sandy Am Pass, to put more stations in the middle elevations, because that's where you're going to find out what's happening that's in the gap.
Awesome.
We had atmospheric rivers hitting California and Oregon, and especially all winter long, one after the other. In previous winters, that almost always meant, if you had a lot of snow on the ground, rain on snow, because those atmospheric rivers originate down in the more southern parts of the Pacific. So why not this year? Because I didn't read about any major rain on snow or flooding events caused by warm rain on deep snow.
I think it's because it hasn't quite happened yet. Well, our snow here in the Northwest, our snowpack has been relatively robust and stable, at least in the Oregon part. In Washington, they've been off the storm track a little bit to the north because those atmospheric rivers have preferred to go to California. So I've heard there has been some flooding already in the Monterey Bay area, the Pajaro River and the Salinas River, and there has been some in the Los Angeles area, kind of where they're getting hit by rain, and there's been some snow, in the mountains around LA. I think it just hasn't happened yet. And if you really want to talk about, lots of atmospheric rivers, I didn't mention it before, I'm not sure it was even on my list. 1861, 62. From Oregon all the way down to California, when people have tried to reproduce what happened in that water year, many atmospheric rivers, of course, they didn't call them that in 1861, that caused flooding, huge flooding in the Willamette that essentially wiped out the town of Champoeg and damaged Albany, Corvallis, Canema, all of these little new settlements, few-year-old Euro-American settlements along the rivers. And it essentially flooded the Great Valley of California, that supposedly you could sail a boat from Bakersfield to Redding or something like that. That's what they think of as about the worst case scenario for California. And I'm not sure this year is going to do that, but I think once again, like I said, once it starts getting warm and sunny and that snow starts coming off the Sierra, especially, they're going to have more flooding problems down there.
Right. Excellent question and fascinating work, Matt. Thank you for presenting that today and broadening our understanding of geology and meteorology as well. And also just I really appreciate all the questions and the conversations with Alyssa and Carrie and Andrew. So thank you.